folks are here. There we go. All right. Good morning, folks. We've got Arlene online and Viviana here in person. And that's all we got today. Just the two of you. Was that? All right. So today is going to be a little bit fancy. We're gonna do some calculator solving today. Now, we finally got introduced to quadratic functions, right? And we saw that yesterday with the graphing of them. And now, if I can find 6.2, the next step would be to use those graphs to actually solve a quadratic equation, right? And as I mentioned, our method yesterday of graphing by hand was quick, simple, not super accurate. So if you were to try to solve, as I mentioned, it's not the best way. You don't want to try to solve something with that graph. You're not going to be accurate at all. But let's assume you did have a better graph. What could you do? Well, as I mentioned before, the solutions to a quadratic equation is where the function crosses the x-axis, the zeros of the function or the roots. And this only happens when you set up a quadratic equation. You're looking for, hey, where does the function equal 0? So when you're asked, hey, solve this quadratic equation, first you got to make sure that your function is equal to 0. All right? Every once in a while, they'll try to trick you and be like, hey, solve this. And you'll be like, oh shoot, it doesn't equal 0. What am I going to do? Don't panic. You just need to do a slight algebra step. Subtract 5 from both sides, right? So we can move that 5 to the other side. Now it becomes negative, and now all that's left here is 0. Okay? So that's the setup. We're looking for quadratic function equals 0. Instead of y equals, we have 0 equals. Right? So once you have that, you can then graph the part that's not the 0 and find where the graph equals 0. And you have a couple possibilities when that happens. First off, you could get two real solutions. You could get the parabola crosses the x-axis at 2 points, just like that. Or, as I've summarized in this table here, this is the takeaway. Right? If you're going to add anything to notes, this would be the thing to write down. What are we looking for? When we're graphing, we need this to happen. Two real solutions. Or our vertex could be the solution, and we get just the one. The vertex lands on the x-axis. It is our 0, and we get that one and only one solution. Although technically it's really two solutions in one. It's a double solution. Right? It's just the two solutions are the exact same number. It'll make more sense when we get to further polynomials and we have rules for how many solutions there should be. There should always be two solutions for a quadratic. It's just sometimes the two solutions can be the same number that's allowed. And you get this double where it's on the vertex there. Again, we'll put that in a larger context when we get to the rest of the polynomials. Or you could totally have this happen where the parabola is entirely above the x-axis and going up. Or you flip it around, it's entirely below and just goes further down, and it never crosses the x-axis ever. In which case you have no real solutions. This is why they put that word right there. There technically are solutions. There's always two solutions. They're just not always that pretty. Okay? And we'll see, I think October. I don't remember. It's on the schedule. We'll hit the complex numbers. We'll learn about, what do you go beyond real numbers? Right? So those will be complex solutions, not real solutions. We're not dealing with those right now. Because you can't get them from the graph at all. Right? Which ones can we get from the graph? Only these guys. Only these. Now, notice the book's technique here seems to be, here's the equation, make sure we set it equal to 0, create a table, graph those points. They do more than just the 3. You need 3 to create a sketch. 5 points creates a more accurate parabola. And that's what they tend to do here. We get all 5 points there. Even when there's no solutions. Oh, can't find them. But even when there's 2, how lucky do you have to be for it to intercept right on the graph grid so that you can actually tell what the number is? Right? More often than not, they're going to end up in, I think we got one here. You can't tell exactly where those hit. Maybe a third of the way between the markings. So the answer is about a third and 3 2/3. Right? That's my estimate there. I have no idea. 1/3, decimal form, that'd be 0.33333. Maybe the answer is 0.3208. I don't know. Right? There's no way to tell from that graph. And there's no way for you to draw a better graph to get a better graph would be slightly more accurate. You can get a better answer, but it's never going to be perfect. All right? However, we have the technology. We can get a much better estimate, even when they don't hit the right on the intersection on the graph paper. And that's what we're going to do today. So I'm going to walk you through how to solve these with the graphing calculator. Okay? Because that's all the technique there is, right? The rest of this section in the textbook, this is the takeaway. Understand what possibilities are, and then you would just do it. All of these problems, the exercises ask you to, okay, here's the equation, solve it via graphing. And that's my worksheet practice for you today, is to solve the equations via graphing. We'll find better techniques that work possibly faster, okay? Possibly more accurately, but we at least want to get an idea for the visual people. Here's what the solutions look like based on the graph. But we're going to do it with the calculator. So I have the calculator app. Yeah. Let me get it on screen. There it is. Turn that screen off. All right. Now, the trouble is I got to have my mouse over there. And thing. Not sure. It's about back to capture cursor. Oh, there we go. All right. So on your calculator, right? You're gonna. Yeah, that's great. Okay. Right, from the home screen, we're solving via graphics. So clearly, we need to graph. So we're going to go to the y equals. I am going to pull up one here. We'll just do example 2 from the text. You saw it on screen before. So we're going to type our equation. I've got, let's see, it looks like 8x minus x squared equals 16. Well, we can't leave it as much. Equals 16, so we got to move that over. So I'm just going to go in the order they appear. 8x minus x square button. Oh, that's the inverse. Whoops. Over, delete. Square button. Okay. You're squaring the exponent. Now you've really done it. There we go. Clear the exponent. And I gotta start over. This thing is being too fancy for me. I'm used to the old school one. All right. Start again. 8x minus x. Just the square button. There we go. That's fine. Okay, and then if we move that 16 to the right-hand side, it would be a minus 16. It's not in standard form. It's not in order. The x squared term should go in front of the linear term. That's okay. It doesn't matter on the calculator. Don't worry about it. The thing to worry about is to make sure that that sign of the 16 is correct, because I had to move it from the equation originally given. Right? That's this example, right? Right there, right? We're moving that 16 over. Okay? I'm going to find my mouse again. Okay. Now we've got that. We can graph it. All right? I always like to go with a zoom 6, and it'll just give us our default window. And now we can see that it hits, looks like just one spot right about there on the vertex. So from this, I'd say, hey, use that our graph by hand tools. Let us find the vertex with a fairly simple calculation. So from here, you could do that. Right? Once you see it on the calculator, say, oh, it's just the vertex. Compute, right? By hand, it might actually be faster, because this is going to take several buttons to get us there. So it might be faster to just find the vertex yourself at this point, now that you know that's the solution. But if it wasn't, for any solution, here's what you can do. Notice we have both the graph button, which takes us to this view, and we also have the trace button, which doesn't look a lot different. Right? But what the trace button does is it gives us a little cursor that walks along the function. And we can arrow over and arrow back. And we can start estimating. Like, it looks like it's going to be, try to get y as small as possible. 3.939. Maybe it's 4. Is it exactly 4? This isn't that precise. Because it's going like pixel by pixel. Okay? That's where the pixels landed. That's not exactly our solution. We don't want to rely on that. But we can tell the calculator to find it. We go second trace, takes us to the calculate menu. And I wanted to calculate, in this case, the intersection. Right? We're looking for 0. Wait, 0 is a special kind of intersection. Where it equals 0. Oh, that's on our list. Right? The root, the 0, number 2. Right there. So you just press 2. Find me the 0. And then the calculator is so dumb. It literally needs you to tell it where to look. Right? It can do the calculation perfectly, but you got to tell it where. So it says left bound. How far left do you want me to look? Few clicks. Make sure I'm definitely left of that thing. Sure. Start here and look all the way until there. Right? Give yourself a little bit of room to be sure. And it says, hey, best guess. What do you think it is? Human who can actually see the screen. Right? Right there. You don't really have to move the cursor that far. All right? I've exaggerated a little bit. It can get the job done if you're just a pixel on either side. It'll do it. Okay? I like to stretch it out. It's a few more buttons, but I'd like to be sure that I've actually covered it, because if you mix them up, if you have the bounds like backwards, it'll confuse the heck out of the calculator and it'll freak out and won't know what to do and it'll give you crazy errors. So you don't want to do that. Okay. Then press enter. It'll say, found it. Your 0 is at 4.00000026. Now, what is the actual 0 of this function? If we use our techniques from before, we know the vertex, x equals negative b over 2a, a being the coefficient of the squared term, in this case, it's a negative 1. So 2a becomes negative 2. We have negative b divided by negative 2. b is the linear term, the one on just the x, just 8. Negative 8 divided by negative 2, that's a positive 4. That's a perfect 4. We should get a perfect 4. We would expect a perfect 4, right? This is why it's better. This is certainly better than you, well, maybe in this case because of the vertex. By hand, you'd get it right. But I want you to see the limits of the calculator. It is graphing, it is finding the solution by graphing. It is not computing based on the equation. It is doing this more complex computation that is actually looking at the trend of the curve and where does it hit, and it is working like back and forth until it finds the best result, accumulating decimal points of accuracy, or in this case, inaccuracy. So I would not trust this calculator beyond 3 decimal points. Right? There's a reason we only write so many, okay? Because it uses more sophisticated techniques, because sometimes you'll want to find the 0 of a different type of function that we don't have a method to do by hand. And then you have to rely on the computational techniques. But limitations of this device gives us limitations on the accuracy of those computations. So don't freak out and be like, oh, all the way out to 0, 2. That 2.6 is rounding error. Okay? Ignore that. 3 decimal places tops. And if you see 4.000, 3 zeros after, it's a 4. It's a regular old 4. Okay? Functions exactly how you expect all other 4s to function. So in this case, our 0 is at 4, 0, right on the vertex. Anytime you go, second, calculate a thing. In this case, we want the 0. It'll start prompting that. And after you pick a bound, say, hey, calculator, search between here. It'll create that line as a reminder to you of where you put the left bound. And now I can select the right bound and say, okay, between here and there, find a 0. And I'll be like, I didn't find a 0 between here and there. Detecting no sign change, gives us the result, fully allowed number of iterations. Yep. And that's because I gave it table bound, right? There was no 0 between those points. Yeah, notice it said something about a sign change. It was looking for where the function changes from positive to negative. Right? So I bet the vertex bit, I bet those ones give it more trouble than the regular 2 solutions, because there's not a sign change, right? You only hit 0, it doesn't have a positive value. Okay. Any other questions on how to find solution via the graphing calculator? No? All right, then. Back to today. You have a worksheet then, just filled with equations. All right. Some of them, they've already got the graph for you. So this is just in you reading the graph. Right? Understand that they may or may not be that precise. These ones look pretty okay. In general, if it looks like it goes through the grid point, it goes through the grid. Okay? Don't be like, oh, what if it's like 6.01? Like, it looks like it's 6, it's a 6. Okay? That's fine. But then these, I know the directions say graph by hand. Don't do that. Don't graph them by hand. Do them all with the calculator. All right? Practice using that calculator. This is both quadratic practice and TI-84 practice for you. Okay? And I believe you can, yes, check your solutions there. All right? So you've got the rest of the period to work on that. Other questions, then shut down the YouTube stream.